Okay. Okay. Now you remember we started another converter, which is DC-DC converter. We discussed the idea of DC-DC converter and their applications, and the first type of DC-DC converter was the buck converter, step down, where we're stepping the input down into another voltage, example 12 to 5, 6, 7, and so on. Now, also, we have another converter which is called boost converter, step up. If we adopt the same discussion for the previous one, our task will be more easy here. As you can see here, this is my converter. Okay, here is my supply. It could be battery, it could be rectifier giving DC, it could be solar cell giving DC, and this is my input VD. Also, I have switch, I have diode, I have capacitor, I have inductance. The same elements. I just redistribute them, connect them in different way, I come up with different effect. Rather than I stepping down the input voltage, here the output and here the input, I step it up, increase it. As example, I have a 12 volt, I make it 16, 20, more or less in this way. How the circuit work? Let's see first how it work. When we switch on here the switch, the current will follow through the inductance. And by the way, before I go further, you may think in this way, okay, so it was 12, how it come to become 16 or 18 or 20? From where I got the extra volt? You got it? And you are right to ask this question. From where I got this extra energy? Have a look. When I switch the switch here on the transistor, current will follow through the inductance. This diode will not work anymore because there is short circuit before the diode. And the voltage VD appear across the inductance. As you can see here, this is the voltage of the inductance. VD is the voltage across the inductance. When we switch off, by the way, the circuit look like this. This is the transistor. Okay, it's become short circuit. The diode here is open circuit. Okay, all the voltage apply across the inductance, and this capacitor with this resistance are parallel, but they are isolated from the supply. When I switch off the transistor, the energy stored in the inductance from the previous cycle will be released. So current and energy coming from the supply plus current and energy coming from the inductance released through the diode to the load back. So you look like the circuit becoming this way. Inductance, as you can see here, the diode will be short circuit here somewhere, and then back to the supply. So the voltage here, VL, is the difference between VD and VO, the opposite direction. As you can see here, VD minus VO. Now, the inductance current energy store in the first part here in on state and released in off state. Store, release, and so on. Similar to the discussion how we drive a formula for output to input, we do the same. This VD at this time T on, and VD minus VO at T off. And since T on is dTs and T off is 1 minus dTs, I can substitute, simplify, I come up with this formula. Let's say VO over VD equal 1 over 1 minus D. Let me compare. In book converter, VO over VD equal D. Okay? D always lower than 1. So always VO lower than VD, right? But in boost, we just drive the formula here, as you can see. VO over VD equal 1 over 1 minus D. Okay, have a look. D is smaller than 1, right? Agree with this? Okay. So 1 minus D lower than 1. So 1 divided by something lower than 1 give greater than 1, which means my output greater than my input. So this is the boost effect. This is the book effect. This is the step up effect. This is the step down effect. Easy? Now, as we assume that input power equal output power, so VDID equal VOIO. I can rearrange them. It will be VO over VD equal ID over IO. So I have this one, which is already derived here. I can substitute and rearrange. I got relationship for the current. Now I have two relationships, one for voltage, input with output, one for current, input with output. Also, we learned to discuss the boundary condition between continuous conduction mode and discontinuous conduction mode. Now, the same graph here, this is VL, this is IL, okay? And this is the graph here. We will discuss it in the next slide. I copy it here. We follow the same trend. IL is half I peak, and if we look from this side, okay, this is VD by T on, which is VD by T on, and T on is DTS. So I substituted, okay? And rather than I use VD, I will convert it into VO, because VO over VD equal 1 over 1 minus D. So I can substitute VD here in terms of VO. So I got another shape for the equation. Okay, this is in terms of VD. It is the same, but in terms of VO. Now I can sketch this formula. Let me sketch it for IL boundary. I have this curve. You can see here this curve. This curve is found to be peaked at D.5. It means the highest IL, inductance current, occurred at 0.5. And if you, it's clear from here, if you substitute 0.5 and here 0.5, 1 minus 0.5, 0.5, by 0.5, by 0.5, it gives me 8. So this is ILB maximum. I can rewrite this formula here in terms of ILB max, okay? So the new formula will look like this. So you see, I'm just repeating the same discussion for boost converter. We know that ID over IO equal 1 minus D from the previous IO over ID, sorry, equal 1 over D. So I can rewrite it in this way. Okay. Now let me ask a question. IL, is it connected on the input or output? Let me back. Oh, it's connected on the input. So I input, which is ID, equal IL. It is the same current. So I can find the output current in terms of the input current, which is IL here. I just need to substitute this part here in here and multiply by 1 minus D. It will be 1 minus D square, because already I have 1 minus D and there is another 1 minus D. It will be square. Let me sketch it. I sketch IOB. I got this curve. Now, when I try to find the maximum, I will find it that it's peaked at 1 over 3, 1/3, when D is 1 over 3. So if I substitute here and here 1 over 3, then I got IOB max is this value. Let me rewrite IOB in terms of IOB max. I got this formula. Okay. By the way, I'm just explaining to you from where this formula came. Otherwise, in the problem, in the design, you will use directly the formula. You need this formula as example. You need this formula. I don't ask you about how you drive it, but I want you to know from where it came. Now, also, you remember we discussed the continuous. We discussed also this continuous. This is discontinuous conduction mode, and this is continuous conduction mode. Okay, you can see it's not going to zero for while here we have sometime the current becomes 0, so discontinuity in the current occurs. And the same thing, this is VL, IL, the same formula. In on state, this is DTS, which is T on. Okay, it is the same current, but in off state, from here to here, T off. Delta 1 TS is the time when there is current. And delta 2 TS when there is no current. So usually we ignore it. We did the same in buck converter, if you remember. We did the same. Now, if I want to drive a formula for this mode, which is this continuous conduction mode, I will say, okay, let's multiply here VD by T on, which is DTS, and VD minus VO by delta 1 TS. Rearrange the equation, we come up with the relationship for input-output voltage with respect to duty cycle. See here, delta 1. I have here delta 1. You see? Because now the situation is different. T off is not anymore T off. It's two part, delta 1 TS plus delta 2 TS. Okay. Now, also we can find formula for output current because we know that from this one, we have PD equal PO and ID VD equal IO VO. Rearrange and substitute for VO over VD, similar to the discussion of buck converter. We come up with a formula for current. Relate input to output in this continuous conduction mode. And now I can find ID from this formula, okay, by substituting here. You see delta 1 again appeared, okay. And IO, because the relationship here is clear, I can use this formula and substitute here, this part here, and simplify. I got IO in terms of delta 1. You see? So all these formula just repeating the same discussion, but the differences occurred here in the output voltage, here and here. Now, if I sketch the formula for duty cycle with respect to the normalized of voltage and normalized current, you see here normalized current, this is D, and normalized value for the voltage. I can see there is linear here, linear here, linear here. Okay, this is the continuous conduction mode, and there is non-linear, which is this continuous conduction mode. We found the same almost in buck converter. What is left? What is left is the ripple in voltage. You imagine what we need to do is to design the circuit. My circuit, if I come to boost converter, we have inductance, we have switch, we have diode, capacitor, resistance. Resistance given to you, voltage given to you. I want you to calculate the inductance, it could be capacitance, so to design it, but I need to give you some information. Or I give you inductance and capacitance and I ask you to find the current, the mode, the duty cycle. Let's see this in the next example. He told me here, you have a step-up converter. We need to make sure what type of converter we are dealing with. Now, please just follow me here in this example. It summarizes everything. The duty ratio is adjusted to regulate the output voltage 48. So he told me V out 48 volt. Okay. The input voltage is varied in the range of 12 to 36. VD input voltage 12 to 36 volt. Just a minute, let me compare. 48 greater than both. So that's right, it's boost converter because the output voltage is greater than the input voltage. Great. But also it seemed to be that he gave me the lowest voltage, the highest voltage for input. Two voltages. Okay. The maximum power output, P out maximum, found to be 120 watt. So I have the output voltage, I have the output power, I can find the output current. For stability reasons, it is required that the converter always operate in discontinuous conduction mode. The switching frequency is 50 Hertz. Directly when he gives me frequency, I say, okay, TS is 1 over Fs. So I need to divide to find the duty cycle, to find the time period of the switching. He told me assume the ideal component and capacitor is very large, calculate the maximum value of L that can be used. He wants me to find L. I know that L related to the current. I will use the formula for L and current. But how we work in the example here? Have a look. I list the information given to me in the question, the output. I found TS by dividing here the frequency, and I found the current by dividing the power given over the voltage. I got it. This is the maximum output current. Now next, I have two values. I have two values for the voltage, input voltage. So I expect to have two duty cycles. One for the lowest value, one for the highest value. Okay. Since he did not give me delta 1 or any information can take me to delta 1, I use the general formula for the boost converter, which is V over V equal 1 over 1 minus D. Okay. I will substitute here. VO is constant 48, but once I substitute D for 12 and once for 36 to get D. I got two D's. This is 1, this is 2. Okay, I got 2D. Now, what is next? He told me find the maximum value of L. Now, let me ask a question here. From principles, when we increase the inductance, which is shock, we reduce the current or increase the current when we increase the inductance? Anybody remember? Current reduced or increased? Let me remind you. We mentioned that in level 2 that when inductance increase, it hung the current. Current reduced. Okay, so let me have a look at the output current here in this curve. I have D, how much D? 7.75, this one, and D 0.25, this one. This one, the current is this value, and this one is current is this value. It seemed to be at 0.75. The current is lower than at 0.25 here, which is what we are looking for, because we need to look to the highest or maximum value of the inductance. So we will select D to be 0.75. Now I will substitute here. Okay, I will substitute. Okay. I have lecture. I'm not recording. Just 1 second. Okay, so sorry for this interruption. What happened is you can see here. I selected D to be 0.75. Okay, and I have the current. Let me substitute the current here. TS I calculated. VO I have it. D I have it, which is this 0.75. I substitute to find L. I got this L. You may say, okay, can I do the calculation without looking to this graph? Yeah, you can. You can use the formula twice. Once for this value for 0.75 and one for 0.25. What we come up with? We come up with two values for inductance. Select which one is the highest, which is at the end. It gives you 9 microhenry. Now, one more issue is the ripple in voltage. Ripple in voltage here found to be simpler than boost converter. Why? Have a look. If I come to sketch the current of the diode, when the transistor or the switch is on, diode current is 0. When the transistor is off, the current of the inductance will appear across the diode, which is released, energy store released. This one. The average will be IO. So charge, discharge. So if I come to the formula, which say that dV over dQ over C, capacitor equation, Q equals CV. And delta Q, this triangle here, rectangular here, the distance from here to here, the width is T on, which is DTS. And from here to here is IO, which is VO over R. Let me substitute, this is IO DTS. Let me substitute this by VO over R. I'm here. And I will take, by the way, I will divide by VO because I want it to be in percentage. Then RC, I call it usually tau as the time constant of the circuit, is very simple equation. As you can see here, the ripple in voltage of this circuit is related directly to the capacitor. You increase the capacitor, you reduce the ripple. This is the end of my session. If you have any question, please, you are free to ask.